Okay, so 8th graders. So sorry I can't be there today, but you will have me digitally, I guess, as your teacher. So we're doing 7.4, solving systems of equations. And this may sound familiar to you because we actually did something like this about a month ago, but we did everything graphically. So in 7.4, we actually take the ideas of a graphical solution and then we solve it algebraically. Okay, so if you forgot what all this looked like, I will just show you really quickly here. Okay, so this is 7.4, and we're solving systems of equations. So just remember that a system of equations is like when you have sets of equations that contain two or more variables kind of joined together or kind of linked together as a set. Now, a solution to these systems is this, and I'll quickly type this in. Okay, so there it is. Well, what is a solution, right? I've just kind of written it in there, but again, a set of values that makes all equations true. So if you kind of remember this, remember we did this graphically where we have like an x and a y axis, and I could have one equation kind of point off like this, and another equation down like this. But then my solution was the intersection point for that system. Now, other options that we had, if you recall, sometimes the lines actually never touched each other. And you could actually get two lines that are parallel to each other, they'll never touch, and you'll get no solutions to your system. So we're going to have that in these questions, but you're not going to see it graphically, it's going to be more algebraic. And then the third example that we had discussed back in the day is these graphs. If you have the first line, then I just have to draw it right next to it, but you have a second line that's actually right underneath it, on top of it, and that's when you got an infinite solution, or infinite numbers of solutions. So there's infinite, there was no solution, and there was one solution. So we're going to figure this out algebraically in a few seconds here. All right, let's try it. Okay, so here's our first example here. So this will be example 1, and here is going to be my my system of equations. So our first system is going to be y equals 4x minus 6, and the second equation is going to be y equals x plus 3. So if you kind of recall this situation from a graphical standpoint, remember these are two linear equations. The first one, maybe I'll use my pointer tool. All right. Remember that this number here, that's going to be the slope of the line. So that's 4, y-intercept, slope, y-intercept. So this, again, in a general sense, again, thinking through this, we get a line that goes up really sharply and another line that's just a little bit more flat. And what we're trying to do is find the intersection point. So we're doing this algebraic now, not graphically. So how is this going to work? Okay, so when you're thinking through this problem, you gotta realize that the actual intersection point is going to be a coordinate point that is shared between the two lines. Okay, so if the y-coordinate is shared between the two lines at the intersection point, we can basically think of it like this, that at the intersection, 4x minus 6 is going to equal x added to 3, like so. Because there's going to be a y-coordinate that's going to be the exact same y-coordinate between the two lines. Okay, so if you write it like this and you make the two equations equal to each other, because the y equals the y, then you can write 4x minus 6 equals x plus 3, and you can solve for y at this point. So that's what I'm going to do. I'm going to subtract the left by x, left side by x, left and right by x, so that's going to make 3x minus 6 equal to positive 3. I'm going to add 6 to both sides of the equation, add 6, that's going to be 3x equal to 9, divide by 3, x equals 3. So what I know then is that my x coordinate is 3 at the intersection point. And now since I know one of the coordinate points, x, I can take this number and substitute it back into either the first or the second equation. Doesn't matter because they're going to be the same. So I'll just choose the second one. It's a little bit easier. So what is that equation? Y equals x plus 3. We just said at the intersection that x is going to equal 3. So 3, substitute 3, add 3, so y is equal to 6. So that means my intersection is at 3, 6, and that is the solution to my first system here. Done. Okay, so in this third example, things are getting a little bit more complicated because now instead of using 2 lines in here, I got 3 lines. Okay, so that makes things just a little bit more complicated. Now again, if you can kind of imagine what's happening, I just draw a rough sketch of this. Just try imagining line 1, a line 2, and then say a line 3 like this. And my intersection point, the solution to my equation is where all 3 lines meet. Okay, so the process is actually kind of similar to the previous question. And so I'm going to show you what we're going to do here. Okay, so in this case, I'm going to take equation 3 and equation 2, and I'm going to rewrite them kind of solving for x or making x equal to something. Okay, so x plus 4y equals negative 10. If I subtract by 4y, subtract by 4y, okay, then what I get is x equal to, and that's a negative, so negative 10 minus 4y. My second equation started off as x minus 3y equal to 11. Okay, but if I add 3y and I add 3y, then I wind up getting x equal to 11 added to 3y. Now at this point in the problem, I have x equal to something, I have x equal to something. And kind of following the same reasoning as the previous question, I could make these two equations equal to each other because at that x point, that's where we're going to get this intersection. So that's what I'm going to do. So I'm going to make negative 10 minus 4y equal to 11 added to 3y like so. So I could solve an equation in y. So I'm going to add 4y first because I don't like working with the negative number. So that's going to be 11 added to 7y on the right. And then on the left, I have minus 10 minus 4y plus 4y. So that's going to be just minus 10. I'm going to subtract 11 here. And now I don't have a point. I have to work with the negative. So negative 10 minus 11 is minus 21 equal to 7y. Divide by 7. Divide by 7. Y is going to equal negative 3. So I know then, even though I drew it wrong here, that the y point is at negative 3. And all I have to do next is take this point, substitute it into any of those equations, and I can figure out what x is going to be. So I'm going to do that. I'll just pick equation 2. It doesn't really matter. Okay, so equation 2 is x minus 3y equal to 11. If I take x minus 3, and I now use the number that I found for the y-coordinate of the intercept point as negative 3, I get y minus 3 times negative 3, which is going to give me x added to 9 equal to 11. Subtract 9, x winds up being 2. So then my solution to this thing, believe it or not, the 3 lines will meet at 2 and negative 3, like so. Done. So you can try this one. It's not as complicated as the previous one, but it still illustrates a similar point. Okay, you start with 2 linear equations. Okay, and I want you to find the answer to this. Go.